So we're gonna start with horizontal asymptotes, okay? So let's just get this going. Okay, and so an asymptote of the form y equals b is a horizontal asymptote. Okay. So recall from our discussion about horizontal and vertical lines, y equals b is the form of a horizontal line. Okay. So remember, an asymptote is a line, and horizontal asymptote is just an asymptote that is a horizontal line. All right. So that's not too tricky of a definition. And then we also have another one called a slant asymptote. Okay. So let's just get with that down. So let's just get that definition down. An asymptote that is neither horizontal nor vertical is a slant asymptote. All right, is a slant asymptote. Okay. Hold on 1 second. Make sure my microphone is up enough. No, it's not. Okay. Sorry, the volume on my mic went down. So I just raised it. Hopefully it's not too loud for you guys. Are you guys able to hear me clearly? Is it loud enough? Okay. All right.
Yeah.
All right. Thank you. Cool. Okay. So it's going to be neither horizontal nor vertical. So it's going to be of. So this is a period. So I'm just writing a new sentence. This will be of the form y equals mx plus b. But since it's not horizontal or vertical, we need to stipulate that the slope is not 0. Okay. Because if the slope was 0, if m was 0, it would fall under the definition of horizontal asymptote. Okay. So slant asymptote is when it's a line with non-zero slope. All right. So let's just kind of attach pictures to these definitions. What do these things look like? Okay, so first one, let's get the horizontal asymptote going. Okay, so this dotted line here, that is a horizontal asymptote at y equals 3. So you can see that as the input x approaches infinity, the graph is coming arbitrarily close to this dotted line. Okay, and also as x approaches minus infinity, as we travel out on the left, as we travel out towards the left, the graph is also becoming arbitrarily close to this dotted line. Okay, and when I say arbitrarily close, it means that the distance between the graph and the horizontal asymptote is approaching 0. Okay, so that's just a horizontal asymptote. And now let's look at a slant asymptote. So these are kind of cool. Okay, so let me just put this down. Sorry, this thing gets a little annoying. Okay, and again, it's the same principle. So now the graph is becoming arbitrarily close to this line here. But this line, so this line is 3x plus 1. It's a slant asymptote. Okay, so you can see the graph is getting arbitrarily close to the dotted line here and also over here. Okay, so that's what a slant asymptote looks like. So we're just going to be investigating how to find slant asymptotes and horizontal asymptotes of rational functions. Okay, so let me just write that. All right, so what are we going to be doing today? So we will be examining Examining. Well, did I spell that right? Examining? I think so. We'll be examining horizontal and slant asymptotes of rational functions. Rational functions, so P of x divided by Q of x. So, okay. Okay, so just recall the definition of a rational function. It's a polynomial divided by a polynomial. So both P and Q here are polynomials. All right. All right, so let's see how this plays out. Let's see how this plays out. All right, so we're just going to get right to it. Okay, so this is going to depend on the degrees of the numerator and denominator. Okay, so that's what's going to determine whether we're in a horizontal asymptote or slant asymptote. We need to examine the degrees of the numerator and denominator. Okay, it's going to depend which one has a higher degree. All right, so here is case one. It's gonna come in cases. So case one is when degree of denominator is strictly greater than degree of numerator. Okay? So when this happens, when the degree of the denominator polynomial has a strictly greater degree than the numerator polynomial, there is a horizontal asymptote at y equals 0. Okay, so that is the conclusion here. All right, you get a horizontal asymptote at y equals 0. Okay, so here's just an example of such. How about this function? F of x equals 4x plus 2 divided by x squared plus 4x minus 5. Okay, so just note that this rational function definitely satisfies the conditions of case 1. The degree of the denominator is 2, and the degree of the numerator is 1. Okay, so we have a higher degree in the denominator. Okay, so this function will have a horizontal asymptote at y equals 0. All right, so let's just go and get a picture of this guy. Okay. Okay, so what we have graphed here, I believe, I'm like fairly certain the graph here is of the function 4x plus 2 divided by x squared plus 4x minus 5. And you can see that we do have this horizontal asymptote at y equals 0. Okay. And so someone brought up last class, can a graph cross an asymptote? Yeah, absolutely. Look, the graph is crossing the asymptote right here. All right, so that is allowed. Okay, it's a common misconception. But the graphs can cross asymptotes. Okay. All right, so that's case 1. Okay, now let's look at case 2. Let's look at case 2. And there's going to be 3 cases. Okay, so we just did when degree of denominator is greater than numerator. How about when the degrees are equal? What happens when the degrees are equal? Okay, so case 2 is just that. When degree of numerator equals degree of denominator. Okay. So this is what it looks like. So I'm not going to say the conclusion just yet, but if the degree of the numerator and denominator are equal, you're going to have something like this: an x to the n plus dot 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 plus a1x plus a sub 0 divided by bn x to the n plus dot 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 plus b1x plus b sub 0. Okay, now just note that in the numerator and denominator, we have polynomials of degree n. Okay, they're both of the same degree. All right, so what is the conclusion? Okay, here's the conclusion, comma. There is a horizontal asymptote at, okay, so this is kind of cool, at the line y equals an over b sub n, a sub n divided by b sub n. Okay, so what you do is you take the ratio of the leading coefficients. Okay. Okay. Okay, so you do not take the x to the n. You just take the ratio of the leading coefficients. Okay, so in quotes, it's the ratio of the leading coefficients. All right, so that is the conclusion. In this case, when the degrees are equal in the numerator and denominator. All right, so we just have one more case. Oh yeah, first, let me just get an example, of course. So an example of a function in this case 2 scenario, look at f of x equals 3x squared plus 2 divided by x squared plus 4x minus 5. Okay. And you should see that the degree of the numerator and denominator are the same. They're both 2. So we're definitely in this case 2. All right. So this will have.
Hi, Mr. Roberts.
Hello, Saeed. How are you?
Good, how are you?
Okay. So this will have horizontal asymptote. At, okay, so you just take the ratio of the leading coefficients. Would someone like to fill this in for me? Would someone like to tell me the ratio of the leading coefficients? Where will this have a horizontal asymptote?
3 over 1, or 3.
Yes, exactly. Excellent. Thank you, Eli. Yeah, and we'll have it at y equals 3 over 1, but we usually don't write things over 1 because it's just itself, so it's just going to be y equals 3. Excellent. So horizontal asymptote at y equals 3. Very good, very good. So I do have an image for this, apparently. Oh, right. Okay, I guess this is it. Copy. All right, so, oh yeah, so was this the example from before? Something like that. Yeah, anyways, this is the same picture from before, but yeah, so look, you can see we do in fact have the horizontal asymptote at y equals 3, okay? Okay. So we got this behavior going on out here. We're approaching the y equals 3 line, and also we're approaching it over here. All right, so that is case 2, and we just have one more case. Case 3. Case 3. And of course, stop me if anyone has any questions, of course. Okay. Case 3. Okay, so this is when the degree of the numerator is 1 more than the degree of the degree of the denominator. Okay, I know that seems quite strange, like why just 1 more, but I'll explain. So case 3, when the degree of the numerator is 1 more than the degree of the denominator. Okay, so that is the scenario when the degree of the numerator is just one higher than the degree of denominator. What is the conclusion? What's the asymptote behavior? Okay, so here it is. There is a slant asymptote. Okay, so here's where the slant asymptote. There is a slant asymptote at the quotient obtained by dividing the polynomials. Okay, so remember, a rational function is going to be a polynomial divided by a polynomial. In case 3, we have that the degree of the numerator will be one higher than the degree of the denominator, and we can find the slant asymptote just by dividing the polynomials, okay, and looking at the quotient. So the quotient you get, that will be precisely the slant asymptote. Okay, so let's do an example. Okay, example. So this rational function, f of x equals 3x squared minus 2x plus 1 divided by x minus 1. Right. So just make note that we are indeed in case 3. The degree of the numerator is just one higher than the degree of the denominator. Degree of numerator is 2, degree of denominator is 1. All right, so we are in case 3. Okay, so what case 3 is telling us, we actually need to carry out this polynomial division to find the slant asymptote. Okay, so to find the equation of the asymptote, perform the division. Okay, perform the division. All right. I don't know about you, but I would definitely prefer to do synthetic division on this guy. Maybe some people will disagree, like Eli was telling me earlier, but I just, in the interest of time, I'll just do synthetic division on this, okay? So for synthetic division, remember you just take these coefficients of the numerator, so I'll just write down 3, -2, and 1. I put this half box thingy, and then our k value here, be careful, we have an x minus 1 in the denominator, the k value will be +1, okay? So I put a 1 here. All right, so now let me just carry out this division, bring down the 3. 3 times 1 is 3, -2 plus 3 is +1, 1 times 1 is 1, and 1 plus 1 is 2. Alrighty, now, all we care about right now is the quotient. We do not care about this 2, okay? The 2 is the remainder, so that doesn't matter right now. We just care about the quotient. And that's everything to the left of the remainder, okay? So the quotient here, so the quotient is 3x plus 1, right? So remember, these numbers here are coefficients of your quotient. That is the slant asymptote. That's it. The quotient 3x plus 1 is the slant asymptote. Okay, and that's all there is to be done. Okay. So I do have I think I have the last picture. I think it's just the same picture from before. I don't know why I put them twice, but anyways, this is a graph of the rational function from up here, this guy. And yeah, so it has this kind of asymptote at the line 3x plus 1. Okay. So those are all the cases. So now you may be wondering, why are we not caring about when the degree of the numerator is like 2 higher than the degree of the denominator, or 3 higher or 4 higher? So in that case, your quotient that you obtain after doing the long division is not going to be a line anymore. Okay, so if you do a polynomial of degree 4 divided by a polynomial of degree 2, your quotient will be a polynomial of degree 2, which is a quadratic. That will be your asymptote, but a quadratic function is not a line. So that technically does not satisfy the definition of an asymptote. All right, so that's the reasoning why we just consider 1 degree higher in the numerator. Because if you do 1 degree higher in the numerator than the denominator, your quotient will always be a linear function. It will be a line. Okay. All right, so I just have some examples. Oh yeah, all right, okay, so now yeah. Okay, so first I just have like a nice little summary. So summary, I think is it here? Oh yeah, here we go. Right, so what I have here in this box, this is just case 1, 2, and 3, just in a nice little, just in a nice little box here. All right, so horizontal asymptote can be determined by looking at the degrees of the numerator and denominator. So if degree of numerator is less than degree of denominator, we have a horizontal asymptote at y equals 0. If the degree of numerator is greater than degree of denominator by 1, no horizontal asymptote, we get a slant asymptote at the quotient. And in the last one, degree of numerator is equal to degree of denominator, you get a horizontal asymptote at the ratio of the leading coefficients. All right, so there's just a nice little summary of case 1, 2, and 3 that I wrote above. That's all. Very cool. All right, so we're just going to do just some practice examples, and that will finish this. So examples. All right, so here is the question. Identify the horizontal / slant asymptote for each function. So I'm just going to write down a few functions here. Okay, so identify the horizontal / slant asymptote for each function. And here are the functions that I'd like you guys to consider. So A, this will be 6x to the third minus 10x over 2x to the third plus 5x squared. B will be x squared minus 4x plus 1 divided by x plus 2. And the last guy will be x squared plus 4x divided by, oh, sorry, just having trouble reading my handwriting. Yeah, x cubed minus 8. Excuse me. Yes, x cubed minus 8. Okay, so let me just work through these examples very quickly. So, solutions. Here we go. So let's look at A first, shall we? So A, so you can see that the degree of the numerator is 3, degree of denominator is also 3. So we're in case 2, so let's just make note of that. So degrees are equal. So that was case 2, if you look above. So what do you do in that case? You take ratio of leading coefficients. So take ratio of leading coefficients. All right, so the ratio will be, we're just going to take 6 divided by 2. So it's 6 over 2, which is 3. And that's where our horizontal asymptote occurs. So we got a horizontal asymptote at y equals 3. All right, so that takes care of that one. All right, so any questions? All right, let's look at B. Okay, so B, remember, we need to examine the degrees of numerator and denominator. Degree of numerator is 2, degree of denominator is 1. So it looks like to me that the degree of the numerator is just 1 more than the degree of the denominator. Okay, so that gives us case 3, the slant asymptote case. So let me just write this. So we have degree of numerator. So we're on B here, this x squared minus 4x plus 1 divided by x plus 2. Okay, so degree of numerator is 1 higher than degree of denominator. All right, I hope everyone can see that. We have degree 2 on top and degree 1 on bottom. Okay, degree of numerator is 1 higher than degree of denominator. So parentheses, that is case 3. So what do you do here? So you have to do division. So do division. So do division to find the slant asymptote, okay? All right, well, here we go. We just have to carry out this polynomial division. So I'm going to do, again, synthetic division. So I'll take the coefficients 1, -4, +1. Okay, I have 1, -4, +1. Set up this box. My k value is -2. Right, okay. So now let me just perform the synthetic division very quickly. Bring down the 1, I get 1. 1 times -2 is -2. Add up this column, -4 plus -2 is -6. Multiply -6 by -2, it's +12. 12 plus 1 is 13. Excellent. So I don't really care about this last number, 13, because that's the remainder. That doesn't matter right now. All I really care about is the quotient, okay? And that's all the numbers to the left of the remainder. Okay, so quotient here, I think you guys will agree, is x minus 6. Okay, it's x minus 6. Nice. Okay, so there's a slant asymptote right there. There's a slant asymptote at y equals x minus 6. Okay, very cool. And that's it for that one. Now let's just look at our final guy. Let's look at C. All right, so what's going on with C? So we have the degree of the denominator is greater than degree of numerator, right? Because I have the degree of the denominator is 3 and the degree of the numerator is 2. So I definitely have a higher degree in the denominator. So that was actually case 1. So let me just write this. Degree of denominator is strictly greater than degree of numerator. Degree of numerator. Okay, and so just parentheses, this is case 1 from above. And the conclusion of case 1, when we're in this scenario, is that there's a horizontal asymptote at y equals 0. Horizontal asymptote at y equals 0. All right, so we actually just hit each of the 3 cases with these 3 examples. All right, each of them was either case 1, 2, or 3. All right, so you can expect just questions very similar to this on later on when we get the next homework going and the next exam. Okay, so that wraps up our discussion on asymptotes, okay? So any questions about this material that we did today? Okay, so I'm guessing it was pretty straightforward. I think it is pretty straightforward. Okay, so now we'll move on to just an exam 2 review. I have one question prepared for review. And then if you guys would like to ask me some other questions, feel free. If not, then we'll finish up. Okay, so let's switch gears here. Now we're just going to do an exam 2 review question. Okay, exam 2 review question. Excuse me. Right, so what this question will be, it's going to be to find the domain of a composite function. All right, so this is something that a lot of people had some issues on homework 5, I believe it was. Okay, so I just wanted to maybe go through it again and try and reinforce what's going on. All right, so here's the question. We're gonna let f of x equal 5 over x minus 1. So we're going to let f of x be 5 over x minus 1, and I will let g of x be 4 over 3x minus 2. And the prompt will just be to find the domain of the composition f of g of x. Okay, so this is very important. You can expect a few questions like this on the exam on Thursday. All right, so let's just try and, yeah, so hopefully this is kind of clear. So let me just make note, when we're given a question like this, you actually don't need to compute the composition. You don't need to actually plug in g of x into f. You don't need to do that. However, what you do need to do is you need to find the domain of g, find the domain of f, and then do some other things. So let's just go through the process. So the first thing you need to do is find the domain of the inner function g, okay? Domain of g. Okay, so the domain of g, we have a rational function, 4 over 3x minus 2, and we need to make sure that the denominator is never 0. You cannot divide by 0. Okay, so you need to do is you need to set 3x minus 2 equal to 0, solve, and then exclude that solution from your domain. All right, so 3x minus 2 equals 0. This will give you a solution of x equals 2 over 3. Okay, so the domain of g is all reals, all real numbers except x equals 2 over 3. So I hope everyone agrees with that, because if I were to plug in 2/3 into g, it would cause me to divide by 0. Okay, so it's not in the domain of g. Okay, very nice. Next, we need to find the domain of f. Okay, so next step, domain of f. Okay, we're in a very similar situation. F of x is a rational function, so we need to make sure that we're not dividing by 0. So you set the expression in the denominator equal to 0 and solve, and exclude that. Exclude that. So yeah, I mean, you can pretty much just do it quickly in your head. You need to solve x minus 1 is equal to 0, and this gives you the solution of x equals 1. Okay, so domain of f is all real numbers except x equals 1. Okay, that's that. We're not done yet. We're not done yet. Now, the third and probably most important step is you need to solve g of x is equal to 1. So you solve g of x is equal to 1 and exclude this solution from your domain. Okay. Exclude this solution from domain.
Because there's no restriction on the other two functions for domain, right?
No, there are
Oh
restrictions.
no, I mean other than those two exceptions. I mean.
Right. So we have and we have a restriction here. We can't be 2 over 3, and we have a restriction here. We can't be 1. Okay. Yes. So this is what we do. We solve g of x equals 1. That will give we solve the equation. That will give us some x value. That x value we have to exclude from the domain. All right. So let's solve it. So we have 4 over 3x minus 2. And we set it equal to 1 and solve. Okay, so this is a rational function. No, this is a rational equation. Excuse me, this is a rational equation. What you do in rational equations, so remember from a few weeks ago, we need to multiply both sides by the LCD, by the least common denominator. Okay, so the LCD in this case is 3x minus 2, so we multiply both sides by 3x minus 2. All right, so I'm just going to be very explicit here. So we multiply both sides by 3x minus 2. Okay, and what do you get here? Well, that's going to clear the fraction on the left side. So you just get 4. And on the right side, you will just get 3x minus 2. Okay. Okay, so add 2 to both sides. You'll get 6 is equal to 3x. Divide both sides by 3. You will get x is equal to 2. All right, everyone okay with that? Okay, now, okay, so remember the conclusion. We need to exclude x equals 2 from domain. Okay, and I'm just going to highlight why we need to exclude x equals 2 from the domain. I just don't want everyone to just be like following these set of steps without knowing why we're doing it. So what happens if we plug x equals 2 into the composite function? What happens if we look at f of g of 2? Why is this bad? Okay, why is this bad? Well, let's see. So we have f of g of 2. What is g of 2? If I plug 2 into g, I'll get 4 over 3 times 2 minus 2. So I'll get 4 over 6 minus 2, which is 4 over 4, which is 1. So that's f of 1. Okay, that's what g of 2 is. G of 2 is 1. Okay, now look at what we have here. We have f of 1. Let's look at f of 1. What happens if I plug 1 into f? You divide by 0. Okay, so f of 1, this is not defined. This is a meaningless expression. F of 1 doesn't even make sense. Okay, so this is undefined. So that's this whole business of setting g of x equal to 1 and excluding it. Okay, it's because this x equals 2 will create an f of 1, which is undefined. All right, so hopefully that kind of sheds some light on the process. So overall, what are the bad values for this function? Okay, the bad values are 2/3 and x equals 2. Those are their bad values. So overall, we exclude. So overall, we exclude x equals 2/3 and x equals 2 from the domain. Those are our restrictions. All right. We don't exclude this x equals 1 from the domain of f. We just did this as an intermediate step to see what to set g of x equals, to see what we need to set g of x equal to. All right. So you just exclude from the domain of g from up here, and then you exclude from when you solve the g of x equals something. Okay. You don't exclude the number from the domain of f. All right. There we go. And of course, I'm going to ask you guys let's put this in interval notation. So we need to write all real numbers except 2/3 and 2. So here's the domain in interval notation. It will be minus infinity to 2/3 union 2/3 comma 2 union 2 comma infinity. All right, and just notice we have no square brackets around the numbers 2/3 and 2 because we're not including them. All right, parentheses mean they're not included in our set. So this would be the final answer, okay? And you can expect a question of this level of complexity on the exam. All right, something just like this. All right, so that's all I have prepared for the review session. I really just wanted to explain this very thoroughly, all right? And hopefully it makes sense to more people now. So, any questions?
I have one question. Just the bottom line of the domain of composite functions. You exclude g of x, and then you exclude g of x, and then you exclude g of x's domain set to the domain of f of x. Does that make sense? Like you first solve the domain of g of x, right?
Yes, that was up here. Yep.
And then you set f of x to equal the domain of g of x.
I set g of x equal to the excluded values of f's domain.
Right.
And that was this step right here.
And then those two values, that'll be your domain. It will never be three values that'll be in your domain, right?
No, so you can exclude, sometimes you can exclude three values. Like if you're solving a quadratic in step 3 here, you're going to get 2 solutions. So it is possible. But what I was just saying is that your domain restriction in step 2, finding the domain of f, that is not one of your excluded values.
Got it.
It's just your excluded values from G and your excluded values from solving G of x equals 1. But we got this one from step 2. So step 2 is necessary because we need to see what we set G of x equal to. I'm not just
it'll always be that way though.
Yeah, just follow this model and you're going to be good. Okay? Yeah, you exclude your domain of G, find the domain of f, find the bad numbers for f, and set G of x equal to the bad numbers for f. Yeah. All right, yeah, so just follow this model and it should be good. Okay.
Could you show why 2/3 wouldn't work?
Absolutely. Yes. Good. Yes. All right. So we showed. So we showed why x equals 2 is bad. So Saeed, do you see why x equals 2 is a no-no here?
Yes.
Okay. So the next question is, why is 2/3 bad? Excellent. Okay, 2/3 is bad. Okay, so let's just look at what happens when we evaluate this guy at 2/3. So in order to evaluate this at 2/3, I first and foremost, I need to look at G of 2/3. But the problem here is that G of 2/3 is undefined. Reason being, if I plug 2/3 into G, I'm dividing by 0. So this inner guy, this G of 2/3, that is undefined. So f can't even, so f of this doesn't even make sense because the input is not even a defined number. That's why. This makes no sense. I can't apply f to something that's undefined.
Thanks.
Yeah, so hopefully that makes sense.
Yes.
Good, good. Good question.
So I have a quick question as well. So when we are finding the domain of the composite function, not the composite function, but the function, when we have one that's not a fraction, let's say it was x minus 2, it could not be -2 or not -2 too. right?
Are you saying it's a fraction or it's literally
Not a
just
fraction. So it just, let's just say it was like x minus 2.
okay? So remember the things you have to check for: dividing by 0 and taking the square roots of negative numbers. In that function you just told me, x minus 2, there's no danger of doing either of those things.
Okay, I see. So it's just when it comes to square roots and fractions?
Right.
Okay,
So
I see.
those are the only things you need to check for. In that function, x minus 2, there are no fractions. You can't divide by 0, and you're not taking a square root of a negative number potentially. So the domain of that function is just all real numbers. So in your first step here, you would just write domain of G, all real numbers.
I see.
Yeah.
Oh, okay. Thank you.
Yeah, so it still follows the same steps, is that maybe just this step here, the first step, you're going to just have a different writing here. Yeah.
Okay, thank you.
Got it. Got it. Luke, do you have a question? I think you may have had a question.
It was more of a. Do you think we could go over like a quick square root one, just to cover all bases?
Yeah, absolutely. So let's look at find the domain of. Let's look at this guy. Let me just think of one off the top of my head. So like 8 plus 2x. Right. 8 plus 2x over like x plus 1. So this is not a composite function now. This is just the domain of a function. Okay. So there's two things we need to check for. 1, dividing by 0, and 2, taking square roots of negative numbers. So to verify that we don't divide by 0, we need to set the denominator equal to 0 and exclude that. Okay. So you set x plus 1 equal to 0 and solve. This will give you a solution of x equals minus 1. So you exclude this from domain. Okay, we're not done yet. So we have just taken care of dividing by 0. We also need to take care of the possibility of taking square roots of negative numbers. So what you do in this case, you take the radicand, that expression underneath the square root, and you set that to be greater than or equal to 0 and solve that inequality. So you do 8 plus 2x greater than or equal to 0. Solve this guy. You will get 2x is greater than or equal to negative 8, which will give you x is greater than or equal to negative 4. Okay, yes, did I do that right? Yeah, okay. So here are our exclusions. So overall, x cannot be 1, and x must be greater than or equal to negative 4. Our x values must satisfy these two conditions simultaneously. Okay? So how do we write this in interval notation?
So it wouldn't be -1?
Oh, it is -1. Yes.
Oh, okay.
Thanks, Camille. Yeah, -1, definitely. Yes, -1. Yes, good. So our x values, our quote unquote good x values, meaning things that we can plug into this function, they simultaneously, they cannot be -1 and they must also be greater than -4. So first and foremost, we know that our domain is going to start at -4 because it needs to be greater than -4 no matter what. Okay, now we can't just go to infinity here because that would include the bad value of -1. So we stop at -1 and put an open parenthesis. All right, we do not want to include -1. So we do that just by kind of putting a parenthesis, and then we put the union symbol, and then we go back to -1 with another parenthesis, and then we go to infinity. So it's like, this is what it looks like on a number line. So first of all, here here is -4. That is fine. Okay, but at -1, we get this little puncture. So we stop, nope, can't go to -1, but everything to the right of -1 is good. So this is our domain. It's like this, it's this highlighted portion. So not the open bubble. Okay, so that's a good example. So yeah, I believe there is an example like this on the exam. Okay. All right, good, good, good. So any other questions? Anything, did you guys have anything prepared to ask me? But I think these are kind of the hardest, maybe like the two trickiest things, finding domain of composites and also finding domains of functions.
I kind of have a question. It has nothing to do with it. Is that a problem?
Yeah, no, go for it. Yeah.
Okay. I kind of have a little bit of trouble identifying like odd functions. It's not like really a question, but like I just think like, can you kind of go over it real quick? I don't know.
Yeah, yeah. Okay, good. So this is, yeah, so there is going to be a question like this on the test as well. So this is good. So are you talking about odd functions in particular, or even or also even?
Even and odd, but I have a bigger problem with odd ones. So
Okay,
I don't know.
so good. Okay, so here's the procedure. So first of all, here's the definition. If f of x equals f of minus x, this is an even function. Okay. Secondly, if f of -x equals minus f of x, this is an odd function. First and foremost, those are just the definitions. Okay. Now, to check for even/oddness, always start off by looking at f of -x. That's always your first step. So you plug in -x and you start to manipulate it, and you see what happens, and you look, okay, do I land at f of x, or do I land at minus f of x, or do I land at neither? What you land at will determine if you're even, odd, or neither. Okay, because both of these definitions, they have an f of -x in them. Okay, I probably should have written this. Oh yeah, hold on. I'm just going to change how this looks. I want to put the -x on the left side. So even is f of -x equals just f of x by itself. So in both of these definitions, you start off with -x as the input, and you see what it leads to. So let me see if I can think of a quick example here. Okay, so let's look at f of x equals 1 over x cubed. Okay. So, and the question is even, odd, not a slash. So the question is, I'm asking you, is it even, odd, or neither? Okay, so what you need to do is you always start off by evaluating at -x. So you look at f of minus x, okay? So that means wherever I see an x in the definition of f, I replace it with a -x. That's all that means. So this is the same thing as -x to the third power. However, -x to the third power is actually the same as, I mean, if you have it in parentheses, it's the same as -x to the third power without parentheses, okay? Because if you raise a negative number to the third power, it remains negative. Okay, awesome, but you can bring this minus sign that's in the denominator up in the numerator, because it's the same thing. And you should maybe notice, oh, look, this is negative. There's the minus sign, and how about what's left? That's f of x. What's left is f of x. So overall, so therefore, we just figured out that f of minus x is equal to negative f of x through these chains of equal signs. Okay, so this is equal to that. So it's odd, right? That's the definition of odd.